In the time it takes to watch this video, the sun will fuse over 500 million tons of hydrogen into helium. That process releases enough energy to power human civilization for tens of thousands of years. Here on Earth, scientists are trying to capture just a tiny fraction of that power. Welcome to the world of nuclear fusion, often hailed as the ultimate clean and limitless energy source. But why do we even need fusion when we already have solar panels, wind turbines, and nuclear power plants? Our global population is soaring. By 2100, there could be nearly 11 billion people, all needing clean, reliable power. Burning fossil fuels at today's rate could raise global temperatures by 3 to 4 degrees, with devastating consequences. Yes, solar and wind are essential, but they're intermittent. We need an energy source that runs 24/7, emits no CO2, and can work anywhere on Earth. That's why fusion is such a game changer. To understand why, let's compare it to what we already use today: fission. Most nuclear plants split heavy atoms like uranium to release energy. Fusion does the opposite. It joins light atoms like deuterium and tritium, releasing energy at a density 4 million times greater than coal and up to 10 times greater than fission. Deuterium is everywhere. Just 1 liter of seawater holds enough fuel to match about 300 liters of petrol. And the main byproduct? Helium. Safe, non-radioactive, and harmless. Unlike fission, fusion doesn't produce long-lived radioactive waste, carries almost no risk of runaway reactions, and if confinement fails, the reaction simply stops. Sounds perfect, right? But there's a catch. To overcome the natural repulsion between hydrogen nuclei, plasma needs to reach 150 million degrees Celsius, hotter than the sun's core. At those temperatures, matter becomes plasma, a super hot ionized soup. No solid wall can survive that, so scientists use insanely powerful magnetic fields, hundreds of thousands of times stronger than Earth-S, to hold the plasma in place. The most famous design is the tokamak, a donut-shaped chamber where magnetic fields act like an invisible bottle. Another approach is the stellarator, with twisted magnetic coils that weave invisible folds of magnetism to keep plasma stable. And instead of magnets, some researchers are using lasers to push the limits of fusion. In December 2022, at the National Ignition Facility in California, scientists did the unthinkable. 192 lasers fired at a tiny fuel capsule. The result? 3.15 megajoules of fusion energy from just 2.05 megajoules delivered to the fuel. For the first time in history, a fusion reaction produced more energy than it consumed. Sure, the facility as a whole still used more energy than it got out. But this is big news. The spark that proved fusion energy is possible. So who's leading the race to make fusion a reality? A massive collaboration of 33 nations in France is aiming for a 10-fold energy gain. 500 megawatts of output from just 50 megawatts in. First plasma is expected in 2035. Meanwhile, private companies like Commonwealth Fusion, Helion, and General Fusion are innovating with new superconductors, magnetic compression, and high-power lasers. Some even claim commercial fusion by the late 2020s, though experts are skeptical. And across the world, researchers are breaking records in plasma confinement. China's East Tokamak held plasma for almost 18 minutes in January 2025. And in France, West just set a record, 22 minutes of sustained plasma in February 2025. Every step brings us closer. But fusion isn't just about electricity. It could transform entire industries, and even life beyond Earth. Imagine large-scale clean desalination, carbon capture at massive scale, green hydrogen production, power for remote and underserved regions, and even new opportunities for space exploration. Here's the real challenge. Even as fusion races ahead, climate change isn't waiting. The IPCC warns we need to cut global emissions in half by 2030 to avoid catastrophic warming. Most experts think commercial fusion won't arrive until the 2030s or 2040s. Every year counts. We are standing at the dawn of an energy revolution. The real question isn't just, can we unlock clean, limitless energy? It's, will fusion arrive in time to save our planet?